Right, so yeah, the afternoon second speaker is Connor Duffin, who's a postdoc in Cambridge and has actually submitted his PhD thesis today. So it's a great cause for celebration, and we're very glad to have him here. So please get started, Connor.
Cool. Thanks, Sam. It's a real pleasure to be speaking to everyone and seeing everyone virtually, at least again. Today, I'm going to be talking about the work that made up the brunt of my PhD, basically the whole thing, barring a couple of examples and so on statistical finite element methods for, in particular, nonlinear and time-dependent PDEs. So I guess the setting is somewhat what Francesca's work that she was just discussing was motivated by. We have like a high dimensional state space upon which you want to run a filtering algorithm. So my talk's going to be a more from, I guess, an applied maths point of view, because I guess that's more of my background. I'm going to be talking through various case studies and general layouts of the algorithms that we're using, and just sort of show off the methods that we've developed over the last couple of years. And of course, this is a joint work with my co-authors and friends, Ed Cripps, Thomas Dembler, and Mark Girolami. So Ed and Thomas were my PhD supervisors back in Perth in Australia, and Mark's now my boss at Cambridge. And I guess if you want the sort of quick summary of this work in a relatively, hopefully readable fashion, just see this article in PNAS, which came out in January of last year. So I guess the motivation behind this work was Ed and Thomas had previously worked on with some oceanographers on using KDV equations types of models to model internal waves inside of various settings in oceanography in back home off the northwest coast of Western Australia. And they had used these PDEs in as I say, in various contexts, but often taking data from them and trying to, for example, learn oceanographic parameters and parameterizing uncertainties associated with these coefficients alpha, beta, and C, which are the physical parameters that govern the flows that they were looking at off the Northwest Shelf. What it's typically used for, the KDV equation, is for internal waves. So these are physical waves that flow between essentially two layers of water density. So you have a less dense layer of water on top and a more dense layer on the bottom. And you'll have a wave that flows at the interface of these two layers of water, or these two bodies of water. And it is typically called the pycnocline. So that's the interface between the two. And you'll have waves that flow across this pycnocline. Now, they use the KDV equation to model these, often taking these parameters as being fixed objects, and we're wondering how to correct for model mismatch that goes beyond, or not goes beyond, perhaps that's a strong way of saying it, but perhaps looking at finding a way to correct for mismatch and finding a way to study PDE solutions which correct for mismatch that doesn't perhaps come from parametric sources. Because it was believed that, at least for these parameter regimes, we had a pretty good grasp upon which what these should be set to. The idea was then obviously not to invert the PDE, so to estimate those parameters, which would be solving this inference problem here, finding the probability distribution of the parameters given the set of data, but instead to study the filtering distribution of a discretized version of this PDE in a somewhat statistically coherent way. And the way that then I guess Mark came into the work was with this statistical finite element method. So a sort of brief summary of the way that we're going to solve this problem is that we're going to, instead of taking a fixed dynamical process as being, or a deterministic rather dynamical process as driving the flow, we take a stochastic dynamical process. To do this, we added on a stochastic forcing term inside of the KDV equation, which somewhat importantly has the same mean value that we were assuming on the right-hand side, so it's just 0. So there's no forcing in the mean. But there was some sort of spatial and temporal correlation structure associated with this right-hand side noise. We assume that this is spatially smooth and delta correlated in time, mainly for computational benefits. It's quite simple and I guess perhaps somewhat intuitive to write out this as having 0 correlations across time. And this sort of lets us frame this essentially as upon discretization, as a vector valued stochastic differential equation, which we can then discretize again using classic SDE techniques to get a state space model. But as I say this, the first thing we need to do is to actually discretize with the finite element method. There's a sort of 4 bullet point summary of this process, is that on the domain upon which we're solving on, which in this case, this is a 1D equation. So omega is just a line, basically. We're going to construct a mesh which discretizes the domain omega with some mesh discretization parameter given by H. Typically for a uniform mesh, so regular with equal elements, this is just the size of the individual elements that make up the interval discretization. For this example over here, the discretization parameter H is typically something like the maximum diameter of any one of these individual triangles here. And it's some way of summarizing how coarse-grained your mesh is to form this discrete approximation to the domain omega. Upon this domain, we're going to define a set of basis functions that have nice properties. The nice properties that they're going to do is that they're compactly supported within a very small region about each of these intersection points. So if you imagine on this mesh, you've got a bunch of points upon which you're creating the mesh on, and around a relatively small neighborhood, again, governed by the mesh size H, these basis functions drop to 0. So perhaps intuitively, this is a basis function set that allows us to imbue some sort of sparsity in the domain because there's not so much overlap between regions upon which these basis functions are defined. So these are quite nice computationally because everything basically ends up being sparse. And as Francesca talked about in her talk, having sparse matrices is really nice when you get into really high dimensional situations. So the basic process with finite elements is that you multiply with a test function, I'm calling these phi j, and you integrate over the problem domain. So this casts then what is an infinite dimensional problem of the PDE is in what is now a finite dimensional problem, and this defines an ODE over the finite element coefficients. If this is somewhat a bit, I guess it's a bit hand wavy as to how I've gotten here, but the main thing is we're going to get a finite dimensional system, and upon time discretization, we can write out this finite dimensional system as essentially this Markovian process where all of our PDE model is encapsulated into this calligraphic M term here. And this defines, if you just set this noise term over here, which is a Gaussian with mean 0, and some covariant structure, if you just set this to 0, you'll arrive at the deterministic PDE and an updating rule, which is given by our chosen finite element discretization. But because of the way that we've structured our model, we've incorporating this stochastic term on here, which says that we should, I suppose in expectation, have dynamics that are governed by the PDE, but with some amount of process noise that is dependent upon what the practitioner sets or can be estimated. I'm not really going to talk about that estimation procedure, but you can just assume that we have some process noise going on that characterizes how much we believe in the dynamics that are evolving on the FEM space. So this framework, I suppose, then defines a prior distribution. And this prior distribution has some sort of, this is conditioned, again, as I say, on the parameters theta of the forcing and also on a set of PDE coefficients lambda. I guess this is an important thing to note, is that we're explicitly conditioning on a set of PDE coefficients, and we're not, as I said in the initial slides, trying to do some sort of inverse problem. We're really just trying to estimate what this solution to the PDE looks like if you condition on a set of data and condition on a fixed set of PDE parameters, because again, it's not the most unreasonable thing to do in the regimes that I'm discussing or the models that I'm discussing to assume that these are quite well known given physical laws that they're derived from. So then to do model data synthesis, we're going to incorporate data via this quite well known, I suppose, observation process, which you would see in Kalman filtering and in similar fields like data assimilation, where at each time we're going to observe a part of the model on a grid, and this grid is going to be ny dimensional. So you can think of this as being like a subset of the entire mesh that we're looking at. Maybe we have this huge mesh and we're only going to observe every 10th node or every 5th node or something like that, or at some set of sensor locations upon which we're solving some big finite element model. And we're just going to assume some additional stochastic noise on top of our parameters, on top of our FEM nodes. Then again, this is going to be observed via the observation operator, which maps from the FEM space, which is NU dimensional, into the data space, which is NY dimensional. And we're going to assume that we have some additive noisy measurements parameterized by the sigma squared, or the sigma n here, which is going to be taken as fixed in this work. So this writing out this gives a state space model, which to this audience, I really don't need to discuss any further, with a nonlinear evolution on the latent space. Again, this is our physical variable of interest, our PDE solution as discretized by finite elements, UN. And then at the same time, we're going to have this data observation process, and we're going to compute the filtering posterior using the extended Kalman filter. Of course, this is amenable to any sort of filtering technique that we would be interested in. I guess the reason that we've gone with the extended Kalman filter is motivated by the sort of the second half of this talk, where we want to scale things up using much higher dimensions, high dimensional models. And it seems like the extended Kalman filter is somewhat preferable in that scenario for uncertainty quantification. But I'll get to that later on. Here, this is a write-up of how we're doing our extended Kalman filter, assuming that we've got some fixed parameters, theta, which are essentially Gaussian process hyperparameters, and then our PDE parameters, lambda. Then we just solve the model and do a prediction step, propagating the covariance via a linearization. And then we do the standard Kalman update, which works nicely in this scenario because we're assuming a linear observation process, and then recursively compute these steps, and you've got an extended Kalman filter. So now I'm going to go through various case studies. And the first one I'm going to talk about is an internal wave study that was conducted many years ago, about 20 years ago now, at my home university, University of Western Australia. And inside of this, we assume that there is some stochastic KDV model that is modeling the flow inside of basically an acrylic tank. So inside of this tank, what you have is a fairly wide tank. It's about 6 meters long and 30 centimeters deep. And inside of it, you have a layer of salty water on the bottom, and this has a depth of H2, and then a layer of fresh water on top, which has a depth of H1. It's initialized by moving the tank so that it can create an internal angle of theta, and it's rapidly brought back to equilibrium where it stays for the remainder of the experiment. And what you can observe after this initial perturbation is that you have waves flowing across the interface between these two layers here. And inside of this tank, the experimentalists who conducted this study were able to do this really nice method of placing 3 wave gauges inside of the tank. And from those, they were able to measure, using a processing technique, the internal wave heights inside of the tank. So we have this spatially sparse data set where we observe only 3 spatial locations, but relatively high frequency measurements. I think they were taken every 0.1 seconds or 0.01 seconds. It's sort of, I think it's 0.1 seconds. Yeah, it is. So we have these relatively high frequency measurements that are taken in time at a spatially sparse way in space. And we want to see if we can combine that data with a FEM discretization of this governing PDE. To give you an idea of what solutions look like qualitatively and how the data compares, we've got the predicted model in blue here shown against the data. Now the data is given in purple. You can see there's some sort of noise associated with the measurements. And at each of the points, you see that there's some gradual misspecification or mismatch between the extended KDV model, or the KDV model that we're assuming, and the observations. You can see that up to about time 150 seconds, it's performing okay, I would say. It's not insanely mismatched, but there is a degree of mismatch present in the model. But at about this time of 150 seconds, you see these soliton wave trains forming. So these internal nonlinear wave trains forming that end up being gradually more and more misspecified as time goes on. And what we think is going on is that there's some sort of misspecified or unaccounted for viscosity parameter or viscosity process taking into account in the dynamics, because you see that our model predictions move a little bit faster and things happen a little bit faster in the model as opposed to the data. So in the derivation of the model, perhaps there was some assumption made on the viscosity, which led to this sort of mismatch occurring between the data and the model. But in any case, it's there. And just to have another look at what the model looks like. So this is the expected value of the posterior mean. I'll look at some other posterior mean metrics in the next slide. But just to give an idea, you can see that this wave bounces back and forth between the boundaries of the inside the tank. And you can see again at about this time equals 150-second mark, you have this sort of initial shock forming and these soliton wave trains forming inside the tank. So you can see that there's this gradual sort of transient behavior at the start, and then you go in, the nonlinear dynamics begin to show themselves and you get these wave trains forming inside the tank. To get a bit more of a better idea of what's going on with the posterior, we can now look at, after running the filter using the extended Kalman filter, we can look at some of various plots to see how it performs. Looking first and foremost at the posterior, at the wave gauge locations, we can see that more or less the misspecification has been, I don't want to say completely taken care of, but it seems to be corrected for quite significantly, given we're doing this, given the information available from the data. Now, I guess it's important to say that in this case, I think filtering methods are somewhat uniquely positioned because of the fact that you can see that mismatches are gradually occurring process, and repeated application of posterior updates to the filtering posterior is probably going to be a thing that allows for data to correct for possible mismatch in the model, because of the fact that it's this sort of long scale, it's this sort of longer term mismatch that appears as opposed to being some initial large scale mismatch between the underlying dynamics and what the data is saying. So again, as I say, this is probably one scenario where filtering methods in particular are perhaps uniquely poised to do a really good job because of the incremental nature of mismatch appearing in these models. And perhaps one of the more satisfying things about this, about these results, was that we were able to reconstruct the wave profile inside of the tank, given 3 relatively sparse measurements inside the domain. I guess it's quite cool because we're now able to reconstruct dynamics given a sort of physical regularization of the problem that would not happen if we were to use, for example, at least I don't think would be feasible to see if we were using some sort of Gaussian process, just perhaps some sort of Gaussian process interpolator, which I guess you could say that this method is an example of. I suppose it's like a physically regularized space-time Gaussian process interpolator, but I guess that's a fairly hand-wavy way of explaining this method. The next example we looked at is the Kuramoto-Sivashinsky equation, which is a nonlinear PDE. Again, but in this case, you can observe spatiotemporal chaos owing to the balance of these 3 terms inside of the PDE. Again, we're going to add on stochastic forcing, and we can see that the amount of mismatch that we can create via tweaking this parameter in a relatively small fashion can be rather significant because of the spatiotemporal chaos and inside of this model. So the posterior seems to correct for the mismatch that happens between the data and the a priori specified model. And this is again quite obviously seen when you look at a quantity like the relative error. So this is the relative error between the posterior mean and the data generating process. You can see the prior shoots up rather rapidly as you see the spatiotemporal chaos come into effect at about time equals 10, I want to say. And whereas relatively, the recurrent incorporating of information available from the data, as you do when you compute the posterior, seems to correct for this mismatch relatively dramatically. And you can see this when you plot the prior mean on the left in comparison to the posterior mean. The dynamics that you see is, again, are vaguely similar up until this initial sort of t=20 point, I guess. And then they diverge rather rapidly, and you see quite different dynamics evolve out of these systems owing to the presence of chaos in there. And you can see that the prediction error is relatively stable across the whole time. And this is like an RMSE type quantity for the filter here. But all these methods, so they're quite nice in that they're able to reconstruct this sparsely observed phenomena and seem to do a reasonable job at combining a priori specified models with these relatively quite high nonlinearity 1D models. But the next thing we wanted to do was to try and expand this out into larger reaction diffusion systems, which are observed in 2 dimensions. The thing that we ended up doing was using a low rank extended Kalman filter, which was sort of motivated by the idea that Gaussian process covariance matrices really only need relatively few eigenvector value pairs to describe the system. And we want to leverage this inside of the extended Kalman filter, because the extended Kalman filter, through doing its linearization step, is able to deal with having this low rank structure relatively easily, I should say. So we chose to write out the filtering posterior as having this decomposition inside the covariance, where we take this as having, instead of a full rank covariance, a low rank covariance with k modes, which is assumed to be much less than the number of finite element basis functions, or finite element degrees of freedom, I should say. Again, as an example to show off this method, we're going to look at this reaction diffusion system called the Oregonator, and we're going to look at an example where we've misspecified the initial conditions and taken, relatively speaking, sparse spatial measurements. To do this, we're going to look at this spiral wave regime with parameters given by these here. So the stochastic Oregonator system, as I said, at the start of the talk, this implicitly defines a prior distribution. And we're going to assume that mismatch only occurs in the V component. This is just a modeling assumption, and mismatch can be induced on either or both components. We're going to compute this posterior distribution over the discretized finite element solution via the low rank extended Kalman filter, and again assume that data is arriving via the same observation process. Just to give a feel of what the mismatch looks like, it's this sort of blurred or Gaussian blurred initial condition, which you can sort of think at as being a diffused initial condition in comparison to the true one. So to look at the posterior means on the top right here, you can see that they seem to do a reasonable job at approximating the underlying data, which seemed like it looks like a fair amount of observation locations, but it's actually about 1% of the state that's observed, just because the way the plots look like, it ends up looking like it's quite densely observed. And the posterior variances seem to do what I would think is a relatively reasonable physical breakdown of the uncertainty, and there's quite a bit of uncertainty around the region upon which we have the highest gradient or the highest change in the dynamics, which is at the spiral tip. And then outside of that, we have this region of moderate uncertainty. And a cool benefit of running the low rank filter is that we automatically have the modes of the covariance as a side computation. So we can look at how the covariance decomposes into regions of decreasing importance, basically. And you can see, as intuition suggests, you have a higher region of uncertainty around the spiral tip, and around regions upon which the dynamics are less certain, we also have these regions around here. And as a final sort of metric for the posterior, we can look at the relative errors. The relative errors seem to shrink down rather rapidly after the initial correction and sit at around 1% or so. And the effective rank of the covariance, which is similar to like the effective number of particles, I think it's the exact same computation that you would do for the effective number of particles in a particle filter. The quantity looks something like this, suggesting that in reality, the covariance is quite how can I say this? Say the amount of information that is inside of the covariance is quite a lot lower than the actual underlying dimensionality of that covariance. So just some conclusions to summarize this work. We presented a statistical finite element method for nonlinear and potentially time-dependent PDEs, and we studied this across various examples: KdV equation, the Kurumoto-Sivashinsky equation, the Burgers equation, and various reaction diffusion systems. It's all been tested on these and seems to perform relatively well in each of these different regimes. Obviously, the obvious extension that we want to look at is into higher dimensional systems and more nonlinear, more chaotic types of systems, like with the end goal being something like Navier-Stokes. I'll end here because I think I've run a little over time, and here are some references for this work. So thanks very much.
Great. Thanks very much, Connor. I'll stop the recording here.